Good day, everyone. My name is Quan Yu Liu. I'm a staff scientist here at Q-Chem Pleasanton. It's my pleasure to introduce Dr. Felix Plazer today. He'll be speaking to us for Q-Chem webinar number 43 on new analysis tools for excited state quantum chemistry. Felix Plazer obtained his PhD degree at University of Vienna under the supervision of Hans Lischka in 2012. Felix went on to Heidelberg at Ruprecht Karls University with Professor Andreas Drew for 2 years, then came back to Vienna to join the Teixeira Gonzalez group. In 2018, he was appointed to a lecturer position at University of Labra. Felix has been working on a wide range of topics in computational photochemistry. He also has contributed to various electronic structure packages, including Q-Chem, TheoDORE, Columbus, MoCAS, NuonX, and Shark. Okay, I'm going to turn this over to Felix.
Okay, perfect. Yeah, then thank you very much for giving me the chance to come here and talk to you about our work in Q-Chem in wavefunction analysis. Good evening or good morning, depending on where you are. So let me just start with the main motivation behind the things that I'm doing here. So if we want to do computational chemistry, and if we think about Q-Chem, first we want to get accurate numbers, then we want to compare our results to experiment, and finally we want to say that we learned something, that we gain some chemical insight. And now if we think about how do we generate those numbers in Q-Chem, of course, we have very nice methods with couple cluster, ADC, TDFT, lots of different flavors, excitation energy, spin flip, then different versions of CI singles with perturbative corrections, extensions, spin flip, and so on, restricted active space methods, exciton models, and so on. So the point is not to discuss these methods, but it's, let's say, if you just use an arbitrary combination of letters, it's probably already implemented in Q-Chem. It's just amazing to see how much there's going on. And then it's not just about the electronic structure method. People are working on multi-scale models, environments, PCM, density embedding, and so on. And even that is not enough, but there are loads and loads of algorithmic efforts just to make things fast. And again, if you look at the Q-Chem manual, you see talk about multiple moments, exchange matrices, linear scaling, and so on. Then when we compare the results to experiments, we can look at linear optical properties, nonlinear optical properties, for example, 2-photon, resonant inelastic X-ray scattering, whatever. And then there's also amazing things in terms of dynamics now, new developments in Q-Chem. But then the question is, so how do we turn all these amazing things into chemical insight? And more often than not, what do we do after we've used these really, really intricate methods? We look at some blobs of color. We draw an orbital, and then we say, okay, this blob is a little bit bigger than this blob. And we say, all right, it's a charge transfer state. And this discrepancy has always struck me, that we put in so much effort up here, but then, oh, sorry, no, disappeared. But then down here, we just kind of look at our blobs of color. And so that's basically, then I want to think about how can we go beyond this? And here I want to discuss two questions. The first one is, can we assign excited state character in a completely automated way? So I don't want to look at blobs of color because looking at blobs of color is tedious. I want to be able to analyze larger data sets, and I want to remove personal bias in doing so. So for example, we might want to think about analyzing structure property relationships in functional molecules, or want to compare different computational methods. And then the second part that I want to discuss is how can we learn about physics beyond the MO picture. So it's not just about making things easier, more rigorous, but how can we really learn new things about our excited state computations? And there, especially, we're talking about crosslinks to other models like exciton theory and valence-bond theory. So now, how is this talk structured? First, I just want to give you 2 examples about the chemistry, kind of why do you want to use libwfa in the first place? And then I'll talk about the Q-Chem specific technical things, the input and the output, and then some concluding remarks. So just to give you an idea, how do these things usually start? You know, a colleague from synthesis comes to me and she tells me, oh, I've synthesized these amazing molecules. You don't have to worry about the chemistry here, but the point is just, that's how it all starts. You know, we have our molecules with our triphenylamine donor, a triazole ring, and then an alkene and a sulfur group here, and we created different isomers, different oxidation states. All right, that's good, but then they try to take absorption and emission spectra and find out that they don't understand the shifts. So for example, here we're looking in the data set, they had 4 isomers, 4 sulfoxides, where the only difference is here we have a double bond in a Z configuration, or in an E, in a Z configuration, and then here we moved this to the 5 position, the triazole ring. And now what they found out is that the emission energies change strongly. So we have the E one is the blue one here, the Z one is the red one here, and then if we want to look at the 1,5 molecule, and we even have to change our energy scale, so this one is way redshifted compared to the others. So here's again the red one for comparison. And then of course the question that he asks me is, why is that the case? What do we start out with? We start out with, we do the computations. So here we have the first 2 ingredients that we talked about in the first slide. So we use a high-level electronic structure method. In this case, we use the algebraic diagrammatic construction. We use a solvation model. So this is something that Jan Meres had recently implemented, state-specific PCM. And if we do this, then we can get the solvatochromic shifts. So here, for example, we look at the excitation energies. The red circles are the emission in the strongly polar solvent, and we see that we have the right trend. We have the E here, and the Z here, and the 1,5 molecule here. So we can, you know, we can reproduce the trends with emission energies, also that there's strong solvatochromic shifts. We look at the dipole moments, and we see that the molecules with the larger solvatochromic shifts have larger dipole moments. So it all makes sense. We can reproduce the data, but we still haven't answered the question why. We still, let's say we still don't have anything to tell my colleague. Why is this the case? And then I guess the first thing that we might want to do in this case is we look at the orbitals, we look at blobs of color, and then, okay, people look at the highest occupied orbital at the HOMO, this is on triphenylamine, then they look at the LUMO, this is on the acceptor side, and then you might be tempted to say, okay, we have a charge transfer state if this one is here and this one is here. But then, of course, when you look further, then you find out that this is only a coefficient of 0.8. Then a second orbital is also involved with a coefficient of minus 0.4. So clearly the frontier orbitals do not tell the whole story. We have some interference here. And how do we move beyond? And what we did in that specific paper is just a very simple way of doing it. We just sum over all the occupied and virtual orbitals involved in the transition, just making sure. I mean, you can't do it in a very simple way, but if you just do the right matrix operations, then you get the density of the excitation hole and the density of the excited electrons, which are similar to the natural transition orbitals. So at this point, we were ready to create some nice pictures. The red things is the density of the excited electron. The hole is always here in the triphenylamine we don't plot the hole, but we see that the density of the excited electron changes. So when we think about how is the wave function altered by the solvent, then we find out that acetonitrile, shown on the right, always pushes the electron much further apart from the hole than cyclohexane. So this makes, of course, sense. A more polar solvent facilitates charge separation, but it's important to notice that this doesn't work together with these very simple models. So they started out fitting this with the Lippert-Mataga equation, which assumes that the dipole moment is constant with the different solvents, and this is clearly not the case because the more polar solvent changes the wave function, pulls the electron over here. So this is kind of the first puzzle piece why the simple models didn't work. And then when we try to understand the difference between E and Z, the thing that we can find out here once we look at everything together is that the Z is curved and the E is straighter, so there's clearly different electrostatics. The E has a larger charge separation, larger dipole moment, just because we have to move the electrons a bit further away from the triphenyl amine group. And the third point that they asked me is kind of what's the difference between 1 and 4 and 1 and 5. This is if we look at this part, then we see, okay, there's a break in the conjugation for 1,4, but for 1,5, this is conjugated throughout, so things are better connected and it's easier to move out here. So to summarize, the electron-hole densities, or similar to the attachment-detachment densities, they provided us a very compact graphical representation, allowed us to tell a nice story, what happens. But the sad thing is that we're still looking at blobs of color, and this is kind of what I promised you at the beginning that I wanted to avoid. So then we can try to go a bit more into the theory, and I think the one thing that really helps for the things that I'm doing here is to think of as things in terms of an electron-hole pair, in terms of exciton theory. So first we think about our molecules divided into 3 different parts, 1, 2, 3, let's say donor, bridge, acceptor, for example. And then the hole is in one part, it's shown in red, and the electron is either in the same part or a different part. And then when we go through it, we could have a local excitation where a hole and electron are in the same fragment, could have a charge transfer state where they're in different fragments. We could have a delocalized but bound exciton or a Frankel exciton, where the electron and hole are always on the same fragment at every instant in time, but it's delocalized, and then we could have charge resonance states where the electron and the hole are always on different fragments, but distributed over the whole, over a larger part. And now that we know kind of what the physics is that we're interested in, then it's not even so difficult anymore to think about the method of doing it. And what we'll look at is, so basically we need to know the mutual probability distribution of the electron and the hole. And I think that's the thing that's a bit counterintuitive and it always takes a time to get used to, is that we really have a 2-particle distribution. So a delocalized state could either be a delocalized Frankel exciton, or we could have a charge resonance state, for example. So we really have to, we don't just have to know where are the red dots and the blue dots. So just the red dots and the blue dots, that would give us the electron and hole densities, but we also have to know where those little arrows are. So we have to think about it in a 2-dimensional way. And what it turns out is that we can just then compute this probability distribution and put those into little squares. So we compute the charge transfer number. And for example, this value is the probability that the hole is in the first fragment and the electrons in the first fragment. This one is the probability that the hole is in the second fragment and the electron in the first fragment, and so on. And then we can represent the excited states with these little matrices, with the charge transfer number matrices, and get the probability for charge transfer and local excitations. And we can represent the structure here. So we have turned the orbital pictures into simple matrices. All right. So now once we have those matrices, then we can go for the assignment of the states. So what we developed here are these kinds of plots. Down here the energies. So you have the excitation energy for the first, second, third state, and so on. Color coding, we use the oscillator strength. So orange is the brightest state, brown is the next state, this one is blue. So here we have the states, and then down here we look at the characters. So we saw we could decompose the excitations. So we have our three fragments: triphenylamine, triazole, and this like the sulfoxide fragment. And for example, we can say if our excitation is only on triphenylamine, then we have a blue bar. If we have a charge transfer from here to here, we do it green, and charge transfer from here to here is red, and everything else is orange. And that way, we turned our pictures of colored blobs into numbers. For example, we find the first state is 60% locally excited on triphenylamine. Then we have a bit of charge transfer to triazole and just a tiny bit of charge transfer to the sulfoxide group. Then we know the next three states are all triphenylamine centered. That's of course something that the spectroscopists already knew, that out here we have the typical TPA band, and then we see there's some more charge transfer here, and some states on the other parts here. And yeah, just to compare, you can see the natural transition orbitals. So this goes from triphenylamine over to the side. This state only stays on triphenylamine, and this state is only on the left. So of course our bars are in agreement with the natural transition orbitals that you might plot otherwise. So to summarize, we can really just press the button, know where the states are they locally excited states or charge transfer states, and then we could go back to the chemistry and use this to find different trends. So I didn't do this here. This is, in this case, it's just a proof of principle, but the point is, once we have this decomposition, with a rigorous decomposition to do whatever we want to do with it in terms of chemistry. So then I want to switch gears a little bit, and this second topic here is about ionic and covalent states. So this is a bit more away from just making things easier, but how can we really find new physics using these tools that we implemented in libwfa. So if we think about it, think of polyenes and polyacenes, and actually most conjugated molecules have states that come in two flavors. Often you call them plus states and minus states, because we have quasi-degeneracies using the orbital transitions. That's why different orbitals interact. And this has been interpreted as ionic and covalent with valence-bond theories. So when you think about valence-bond theory, an ionic configuration is where either both electrons on the left or both electrons on the right. And the covalent configuration is where one electron is on the left and the other one is on the right. So this is the connection that was made, more than 50 years ago. So the fundamental property of excited states is not only kind of interesting from a fundamental point of view, but it is exactly this property that causes huge problems for computational methods. And on the one hand, if we think about ionic states, they cause problems for CASSCF, something that people have been moaning about for 30 years at least. And there's also kind of a problem with hidden charge transfer in TDDFT, that exactly those ionic LA states also cause problems for TDDFT. So this is also something that, from the computational point of view, is something that would be nice if we could get a grip on that. So how do we characterize ionic and covalent states? And there's these very involved dedicated valence bond protocols that we use that construct these configurations. But of course, the question is, can we just do any arbitrary computation and then reconstruct the character from the wave functions? Because then we could use standard quantum chemistry method. And okay, this is a rhetorical question. If we have the wave functions, we know everything that we could want to know. So it has to be possible to reconstruct. The question is just how. So let me just sketch you how we could go about this. So if we think about naphthalene, we compute vertical excitations. Again, here I'm using ADC2. And then usually the states are assigned using 3 types of labels: the multiplicity, the irrep, as always, and then we have this plus and minus label. And what we see now, for example, is that the states with appreciable oscillator strength, this, and this, the raw singlet U plus state. So we kind of have a third type of selection rule, only plus is bright, and for example, the singlet U minus state is very, very dark. So it's very hard to find spectroscopically. And here, let's say out of all these states, I just want to discuss the 4 states shown in red, the B3u states. So when you look at those states, then they all have the same orbital transition. So it's always from the HOMO -1 to the LUMO and from the HOMO to the LUMO +1. And the only difference are the signs. So we have the difference between the spin coupling for the singlet and the triplet. So this is the singlet configuration state function and triplet configuration state function. And then we have the difference in plus and minus for the plus minus states. So we have HOMO -1 LUMO plus, HOMO LUMO +1, or the other way around. And the thing here is that the different, of course, we know that different signs will lead to different superpositions, but the question is, how do we analyze it? And I want to show you later that here we really need kind of sophisticated tools, that you really need a systematic framework. So that's why I think it's a good example to illustrate libwfa. So when you think about it, if the states have the same canonical orbitals, then they will also have the same 1 electron density matrices, same densities, same natural transition orbitals, different densities, attachment, detachment densities, natural transition orbitals, all the same between these 4 different states. But we saw that those have completely different energies, completely different properties in terms of optical absorption. So what do we do? And maybe just kind of to prove you that this is right, we're in a lucky situation, you know, that libwfa allows us to compute all these quantities shown here. So first we can see, is that really right? Kind of this simple picture. So for example, we compute the total excited state densities. Those look exactly the same for all 4 states. But this is not very surprising, because the total excited state densities always look like Christmas biscuits. So, all right, but then we can go a bit more, and for example, look at the difference densities up here, attachment densities and detachment densities for the 4 states. And again, they look almost equivalent. If you squint your eyes really hard, you see a little bit of a difference here, but the important thing is you can't differentiate between the plus and the minus states. So again, also in this picture, we can't really see anything. And then of course, then you go back to the drawing board. So many of the major analysis methods that you might want to do fail. What do we do? And this brings us back to kind of what's my favorite quantity to analyze in many of these things. And this is the one electron transition density matrix, the one thing that I haven't discussed yet. And if you think about the definition, we have the ground state wave function here, excited state wave function here. We connect them with creation and annihilation operators. And then this is the matrix representation, and then we can multiply the matrix representation with the respective orbitals to get a two-body function. And the things to notice here is, first, we directly connect the ground state and the excited state wave function with a matrix element. So we're not just computing differences, but we connect them with a matrix element. And also it's a two-body function. It's a non-trivial two-body function that we have here. And I start out looking at the transition density. This is just the transition density matrix where the electron and the hole are at the same point in space. And now, remember, we didn't find anything interesting before, but if we look at the transition density, suddenly we see that the minor states have transition densities on the bonds, and the plus states have transition densities on the atoms. So suddenly this distinction becomes completely apparent. So yeah, made me happy. And for example, let's say if we look at these transition densities, we know that the transition dipole moment is kind of an arrow pointing from the blue to the red. And then we know here we have a lot of blue, here we have a lot of red. So we know that the transition dipole moment for this B3u state is going to be polarized along the long axis, and it's probably going to be large because the transition density is polarized, and we can see that the other singlet state is probably going to have a very low transition dipole moment because you have all these canceling contributions. But next, we have to delve a bit deeper to understand the energies. And let's say the one thing that I have overlooked for a long time, and I guess is the question, why are there little blobs? So why does the triplet transition density just have very clean shapes, and the singlet transition density has all these blobs around? So to proceed, what we're going to do is we'll look at the CI singles excitation energy, not because CI singles is an accurate method, but because it's better than just looking at orbital energy differences. And we know that the first term is, of course, just the weighted orbital energy difference. But then we have in the CI singles energy two more terms. So this transition density repulsion and this term involving transition density matrix. And if we think about it, then from the point of view of Hartree-Fock theory, this is derived from the Coulomb or Hartree potential. This derives from non-local exchange. But then in the electron-hole picture, these things are reversed for some reason. And this is actually the term that gives rise to exchange splitting, it's exchange repulsion. And this term is the term that gives rise to the Coulomb binding energy in the exciton picture. So this is something to think about. This is a bit reversed. And then we could also think about this as a transition density. The transition density vanishes for triplets. So this one only works for singlets. This works for singlets and triplets. And then when we think about TheoDFT, this one is always included. This one derives from non-local exchange. Okay, now that we know what we're looking for, we can try to think about how to visualize it. So the first thing is this exchange repulsion term, transition density times transition density Coulomb repulsion. And then what I'm suggesting you do here is that we just compute this one integral first. So this one integral is the electrostatic potential induced by the transition density. And then it's just an overlap integral with the transition density. And this produces pretty nice pictures, I think. So up here we have the transition densities. Those are the ones that we had before. And down here we have the ESP induced by the transition density. So yeah, okay. And down here I'm just plotting the numerical value of this integral, so the numerical value of this bit as it flows into the CI singles energy and also into the ADC energy. So for example, what we find here is that the singlet B minus reused, it has a very low electrostatic potential because all these things cancel out. So you see with light blue and yellow, this is very close to 0. And the plus state has a very high electrostatic potential, so red and blue, because we have this more polarized case, and that's why, you know, this exchange repulsion is higher by more than 1 electron volt. That's why the plus state is higher in energy. But this picture also tells me about the question that I asked before: what are these blobs for? And here we think we can compute kind of this term formally also for the triplets. Of course, it only affects the energies of triplets, but we could also compute it formally for the triplets. And the striking thing here is that for the triplet, actually, this term is 3 electron volts higher than for the singlet. So if we would just take the triplet wave function and project it into the singlet manifold, the excitation energy would be 3 electron volts higher. And the one thing that saves us from those 3 electron volts are just these little blobs here, these little changes in the sigma polarization. And we can also see this in the plots. So the triplet ESP is pink and green, which are the very high values, and the singlet ESP is only red and blue, which are the lower values. So that's I think one thing we learned, and that at least I had no idea about before I actually went through the mathematics. And then we can just to continue with a bit more science before I go to the Q-Chem part, is now we have the second term, this is the Coulomb attraction. This is obviously a non-local two-body term that derives from the non-local exchange. How do we visualize that? And here the idea is that we look at this two-body distribution, and we just restrict one of the particles to one atom or one fragment in the system and compute the conditional density, conditional electron density upon the condition that the hole is on one atom. And for example, I'm doing this here. The red bits, so if you look here, the red bits are the probe hole, and the blue bits are the conditional electron densities. And you see the second and third row, they are not interesting. Those are the same for all the states. But what we can see in the first row is that now the plus states, in the plus states, the red and blue overlap. In the minus states, they don't overlap. So plus means the hole attracts the electron via Coulomb attraction. The minus states means the hole repels the electron via exchange repulsion. And then we know that for the plus states, we have enhanced overlap, so more repulsion, more Coulomb attraction. For the covalent state, we have reduced electron-hole overlap. And at this point, we understand the state ordering of the states. The triplets only know about Coulomb attraction. That's why the triplet plus state is the lowest. For a small molecule, exchange repulsion dominates. That's why the singlet plus state is the highest. And those two are in the middle. So in the simple Paris-Apart-Popel model, the 2 minus states would be degenerate once you add electron correlation, and not anymore. But the important point is that we can find out why we have such a huge splitting between the plus states. And just to show you that this is universal, we can do the same kind of game also for different states, and we always find that for the minus states, we can see the red probe hole, and for the plus states, blue and red overlap, and we don't see the probe hole. So this is just a new way of thinking about ionic and covalent states, and I think it would be hard to get to this picture if you wouldn't have these analysis tools available. Just if you're wondering, you can also try to quantify it. We can use the CT measure, which derives from the first part of the talk. So we think about how much charge transfers between the different atoms. We know that if everything is equal distributed, we have 90% charge transfer. So we try to separate this. Below 90% is ionic, above 90% is covalent. And that's really right, that if we use this simple criterion, we get the plus-minus assignment from the literature that people have worked out in more complicated ways. And yeah, and again, we have this thing that the low energy triples are plus state, because plus means more Coulomb attraction, and the low energy singlets are minus states, because minus means less exchange repulsion. All right, so that's about the science that I want to talk to you, just give you motivation for all these things. And then let me just discuss how this looks like in Q-Chem. So the main switch that we have for libwfa is called state analysis. And you set this true, and you get all this amazing analysis. This is available for ADC, for UMCC, and also for TDFT. And it's for various different variants in terms of excitation, energy, spin flip. So I don't have the full picture, but it should be. And if it's not, then it shouldn't be too hard to include it. It's just sometimes one has to be careful to pick the right reference state to treat spin in the correct way, but there's no fundamental reason why it shouldn't be possible. And one interesting thing here is that we have looked at is that because we have the same analysis tools for the different methods, is that we can compare and benchmark the methods. So again, when you compare two methods, it's not like, okay, this blob of color looks a bit like this blob of color, so the method is right. But you can really look at the wave functions in more detail and see, is the amount of charge transfer correctly described, is the double excitation character correctly described, and so on. And this is a paper that Steffi and Mewes did 2 years ago, and I think it's interesting, it's also a bit disconcerting, because it just shows you how messed up things are. So that sometimes even if the energies look good, the wave functions don't. So then if we think about it, some more keywords that I want to walk through, then is how much output do you want? There's something called WFA level, coarse gradient control. It can set this to a lower value if you think there's too much stuff printed out. If you want orbitals, you have those two keywords. So actually the NTO pairs only tells you how much is discussed in the standard output, and this threshold tells you how much is printed to a file. And then yeah, there's things to specify a reference state if you're doing spin flip, because let's say if you do spin flip to the DFT, then you want the analysis not with respect to your cone sham determinant, but you want the analysis with respect to your first response state, which represents the ground state in a spin flip manifold. Okay, then when you look through this and you try to see what quantities are analyzed, then on the one hand we have the transition density matrix, and if you remember, I think in many cases this is the best option you have, because you get some correlations, because we have this direct connection to the CS singles energy. That's why I'm promoting that, and everything that has to do with transition density matrix analysis is called Electron-hole in libwfa language. Then we can analyze state in different density matrices, and in the libwfa language, and these things are called attachment and detachment descriptors. And for example, if you do TDFT, then per default you have the unrelaxed densities, but in the newer Q-Chem versions you can also say CS singles relaxed densities, and then you get the relaxed densities. So just the printout looks exactly the same, only the header is different. So make sure that you're analyzing the right section if you want to do that. And for the files that are printed out, you have an RLX with it. All right, so then how do we plot things? On the one hand, we want to plot orbitals. We can do natural orbitals, natural transition orbitals, and natural difference orbitals, which are the eigenvectors of a difference density matrix. then so you have to specify this, and you can either get them in Molden format, then you can open them in Molden or in JMOL, or you can use this guy equals 2 keyword, then you can open them in IQMOL, or if you really want to, then you can also get the orbitals as cube files. And here the point is that if you have a cube file for every single orbital, then you have huge amounts of output. So then if you really want them, then you also have to do WFA level set to 4. Then you get all the orbitals in cube files, and then you can look at them in VND or in PyMOL, for example. Then if we want to look at densities, so transition densities, electron-hole densities, attachment detachment densities, then so my favorite thing is to use make cube files, so to get cube files in VND and PyMOL. We can also use guy equals 2. Only this is something I still have to look at. I think IQMOL allows you to visualize them, but it shows up under canonical orbitals and not with the excited states. So maybe at some point we should rearrange this so that it shows up in the same place as the natural transition orbitals. And if you want electrostatic potential, so if you remember the discussion about the energies that I gave you, if you're interested in that, then you have to say ESP grid equals -3 and make cube files, and then you get the cube files for these, and then I can show you there are some PyMOL scripts that allow you to create these mappings. So this is the electrostatic potential mapped onto the excited state density. The other part you have are the statistical descriptors. So if you ever run state analysis, you see there's lots and lots of output produced. I don't want to discuss all of it, but let's say one is, for example, when you do a transition density matrix analysis, we have the discussion of the natural transition orbitals. In this case, for example, there's the one dominant NTO with a coefficient of 8.8, and then a second NTO with a coefficient of only 0.15. Then you also get the energies of these NTOs. Then the NTO participation ratio tells you how many orbitals are involved. So if more orbitals are involved, then you have more chances for correlation or interference effect. That's why this is important. Or you can also reinterpret in terms of an entanglement entropy based on the NTOs. So if this interests you, you can look at the paper shown here. Then the next part of the output is called exciton analysis. So I mean exciton analysis, and I'm talking about spatial multipole moments. So this is a way to describe the distributions, how far apart are the electron and hole, how big is the hole density, electron density. Then we can also compute a spatial correlation coefficients. Do we have any excitonic correlation effects? So of these things, the one thing that I think is most important, if you just want to look at one of them, is the root mean squared electron hole separation. Sometimes we also call this exciton size. And if you remember, this is the transition density matrix, and it's just we take the square transition density matrix and multiply it with the square of the electron hole separation. So the Coulomb binding term was the same integral, just with a power of -1, but we can also have this with a power of 2. That's the root mean squared electron hole separation, and we can also have it with a power of 1. This is this linear electron hole distance. So how far apart are they on average? And this allows you to find charge transfer states, but it also allows you to find Rydberg states, because for Rydberg, the electron is just further apart from the core molecule. And one thing that's kind of worth pointing out here that this works also well for centrosymmetric molecules. For example, other things that you might look at, like dipole moments, always vanish for symmetry reasons in centrosymmetric molecules, but there's no problem for this because of this square that you have in the distribution. All right, so then just another tool that you can use in connection with libwfa is TheoDORE. So a separate tool because some things are easier to implement outside. So if you remember this plot that I showed first, this fragment-based assignment of states. This is in TheoDORE. You will need this .om files from Q-Chem and conditional densities that I showed you in the second part that allow you to get electron-hole correlations. These go via the fcheck file. And maybe at some point it would make sense to integrate some of this into Q-Chem or IQmol, but it's the task is a bit different because for the fragment-based analysis you have to know before you start what the fragments are. So that's why it's nice to compute the data in Q-Chem, and then later you can play around with TheoDORE to find the optimal fragments. That's why these two things are separated. So maybe to wrap this up, so we have a large amount of functionality, can plot and have quantitative data. There's some specific keywords that are specific to WFA. Some keywords are borrowed from other parts of Q-Chem, and at first I thought it was good to borrow existing keywords so people don't have to learn new keywords. But of course, I don't know if any of this is confusing, so then please let me know. So let me know if anything is unclear, if you have any suggestions for defaults. So it's of course the question, do we want to have lots and lots of information, but then people feel kind of spammed with too much output? Or do we want that people have to activate every individual analysis individually? Then you have to know all the keywords. So that's kind of the trade-off. And if you think that the trade-off should be done any other way, then please let me know. So okay, to conclude, we have an extended wave function analysis toolbox in Q-Chem for excited states and open shells. It allows us to assign excited state character automatically. We just press a button, know what the states look like. I talked to you about push-pull system, but you can do the same kind of trick whenever you have separate fragments. So you can do it for multi-chromophoric system or transition metal complexes. Then if you remember, if we use the exciton size, we can also find Rydberg versus valence states. We can also use single versus double excitations via the overall norm of the transition density matrix. So these are things that have been used, for example, for dynamics, for extended sampling when you have large data sets, or for method comparison when you just need very precise numbers to compare the different methods. But the second idea is that we don't just want to get things quicker, which is up here, but we want to get new physical insight. And today I talked to you about the valence-bond picture, but then the other idea is you can also do lots of interesting stuff with excitons. So just maybe to show you two recent papers about this. So if you're interested in practical computations, just get some quick and easy pictures, then you can go to this J-Chem paper here. And if you really want to delve deeper into the chemical theory and think about kind of the partial densities and ESPs that I showed you, then you can do the second paper. And then here, I hope a comprehensive list of the people that helped me accomplish this. So of course, it's originated in Heidelberg in the Drive group, and some good interactions with people from Q-Chem, and some help, of course, from my other group, and Patrick, who works with me now. If you're wondering where's Loughborough, it's here, right in the center of England, between Leicester and Nottingham. And yes, it's so many letters and just 2 syllables, Loughborough. Okay, thank you.
Thank you, Felix. It's a really interesting talk. We got several questions here, and feel free to submit more in the question box here. So the first question we got is, for TDA excited state, can we interpret the charge transfer numbers as fragment decomposition under the normalization condition?
I mean, I don't know what the normalization condition is, to be honest.
The fragment decomposition of the trace of the amplitude, the trace of the TDA amplitude and times its transpose equals to 1.
Yeah, I'm sure it comes down, of course, I mean, it has the same normalization condition. So this omega value, which is, oh no, there's no normalization. I guess, sorry. So the normalization is the same, yeah, if that's the question.
Okay, thanks. So question number 2, we can alternatively use attachment and detachment densities to compute the effective electron-hole separation distance. So the question is, how would the result be different from the formula presented in this talk, which is based on a transition density?
Yeah, that's a good question. So again, if we go back, let's see if we go back to TDA or to CI singles, and then we compute the linear electron-hole separation, and then we'll get exactly the same value for the attachment detachment analysis and the electron-hole analysis, and let's say both of those values are printed out. So I mean, you can try it out. Yeah. So let's say it would print the thing that I'm showing here, the linear electron-hole separation would be printed out for the transition density matrix and for the difference density matrix, and this would be the same for CS singles and or TDA. Then if you have some orbital relaxation effects, it's different. That's the first difference. But the thing that's I think more interesting to me is that, for example, that with the difference density, you couldn't compute the second moment, because for the second moment you will need the two-body distribution. So for example, in a symmetric system, you could never do this trick with size.
Thank you. Next question. So how can we check orbital contribution of each atoms in the NTO?
And it's something I have.
The natural transit.
Yeah, so of the individual atoms to the NTOs, I mean, this is something that I have not implemented. Let's say with TheoDORE, you can compute the contributions of the atoms to the overall electron-hole densities. That's something that TheoDORE has directly implemented. If you want to have the atom contributions to the individual NTOs, then it's not implemented, but it's something that I mean, it's a simple matrix multiplication. I don't know if it's scripted in any easily accessible way.
Thank you. So next questions. Is the density analysis presented here implemented in the latest version interface with TheoDORE 2.2?
Yeah. So this is all works with the latest version. I mean that maybe I guess the question is that both I've worked on Q-Chem and TheoDORE on both codes, and the problem is that the mutual compatibility is not great. So if you use the newest Q-Chem trunk and the newest TheoDORE trunk, then it's definitely compatible. If you have an older TheoDORE version and a new Q-Chem, or a new Q-Chem and old TheoDORE, then it's not compatible. I'm sorry.
Okay, so next question. Can the TheoDORE sign or automatically predict fragment schemes?
Actually, there's something that Sebastian May did, so we have a coordination chemistry review where he did some analysis of correlations to predict fragments. So I didn't talk about this, but it's in coordination chemistry reviews if you're interested.
Thank you. So it looks like we don't have more questions. So I would like to thank Felix and all our viewers for watching today. So if you have questions later, you can either contact me or go to our forum. Address is Q-Chem Talk, talkqchem.com, and the video will be. So I've created a topic. You can post under this topic here, and the video will be posted on YouTube in the next few days. Thanks, everyone.
This concludes our webinar. We would like to thank Quantities for organizing, running, and moderating this webinar. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.